Hello once again. This is our 10th and last of the short videos illustrating the visual elements of symbolic logic here at Bellevue College. I'm Mark Story, and I hope this class is working for you so far. If you recall, a tautology is a statement that absolutely has to be true. There's something about the way it's structured that demands no matter what the world is like, this statement has to be true. Probably the simplest tautology would be A or not A. A's true or A's false. Well, it's got to be one or the other. That's a tautology. And what we can do is use natural deduction to prove that tautologies are indeed tautologies. Now, basically, there's nothing new to learn here. You're just using CP and IP exactly the way you did before. All the rules work exactly the same way. This is just basically good practice making assumptions more than anything else. These problems are no harder. Now, this is a real short tautology, just to get an idea as to what it looks like. Now, a lot of students will make a mistake, and you're not going to be one of them, I know, of maybe putting a 1 here and then using this thing. But this is a tautology, and the quick 12-second lecture on this would be this. Pretend this is an argument that has no premises, and this is the conclusion. You wouldn't use the conclusion to get to it, so pretend you just don't have any premises to work with. So you need to start off, just put a 1 out in space. If you can do that, you're avoiding 50% of the problems I see on tests. So just don't use this. This is your goal. This is your target. Notice it's a conditional. You got to make an assumption because you have no premises to work with. You absolutely must make an assumption. So since it's a conditional, let's assume the antecedent. So we indent to the left, and we assume the antecedent A. Now we're looking for S horseshoe A. And because we have no premises to work with, you really are reliant on making assumptions. You have nothing else to work with. Now we're looking for this. It's a conditional, so let's again make another assumption. We'll assume the antecedent of our present goal, S. We indent, once again, write ACP. And now we're looking for an A. Well, you got one right here. Well, but we need one down here. And we don't have a rule that just says yank it down. But fortunately, there's all kinds of ways of doing it. You might find some others. Here's one easy way of getting the A. We take 1 and 2 and conjoin them using conjunction. And what are we going to do now? Simplification. And you might be thinking, well, you already have it up here. What's the point of doing that? Well, I grant it's easy, but we have rules of logic that allow us to do even the easy things. So it looks like if S is true, then A would be. So conditional proof will allow me to pull out and say exactly that. If S is true, then A is true. If S and A. And when I made this assumption way up here, I was hoping to get S horseshoe A. Well, I got one. So now I pull out to the left once again and say if the first line is true, then that last line must be true. Look what we got here. If A is true, then S horseshoe A would be, and I draw that line. You'll notice these rules are working exactly the way they did before. Conditional proof and indirect proof work exactly the way they did before. The only thing that's different is there's no premises up here, so this looks weird. You have to do maybe 2 or 3 problems to get used to it, but there's no premises up here. You're just kind of starting in space. Other than that, it's exactly the same thing. Using CP normally, you draw the lines normally, the rules work the same. Don't be afraid of the problems. Just don't use this. Just make this your goal. And then start off with an assumption conditional proof or an assumption indirect proof, depending on what your goal is. And it won't be a problem.